Okay, here we go. Changing B field magnitude and induced EMF. So this is where we're actually going to change our B field. Okay, if we change the B field, right, we can actually induce field even if the loop stays at the same position and maintains the same area. Okay. So first off, I want to look at this. This is a square loop of wire in the vicinity of a large cable carrying a current I, which varies with time. When the current is positive, the current has direction shown in the diagram. So if it's positive, it's going to the right. If it's negative, it will go the opposite direction. The diagram below on the left shows the cable and loop, and the graph on the below right shows the current in the table as a function of time. Okay. Between which two times in the graph is the current induced on the square clockwise? Okay. Well, we got to understand that I creates B. Okay, current creates a B field. Okay, more current equals more B field. Okay, and direction of of B depends on direction of I. Okay. So to get the current in the square to be clockwise, right, we would just use our hand rule, right? We want it to be clockwise, so we want to go around like that, okay? That's not going to work. It either needs to be a decreasing flux into the page or a increasing flux out of the page, okay? So right now when it's positive, okay, we can see that the B field is coming out of the page above it, okay? Okay. So we would either need to have a the field is going out of the page. Okay. So if the field is out of page, okay. So left hand gives clockwise. Okay. And when will we use our left hand? We use our left hand if it's either we use our left hand if it's decreasing. So we either need a increasing out of page, okay, or decreasing. Sorry, or decreasing into page, right? Well, in this case, we just want an increasing out of page, right? Well, that's going to happen at these times right here, okay? Because notice what's happening here is the current is increasing, which is making the B field stronger. Okay? So at this segment right here from 2 to 4, okay? From 2 to 4 seconds, that's when the current is increasing, right? Which means that B field's increasing, which means that it's going to go clockwise, right? Okay? Suppose that the current in the cable alternates between negative 10 and positive 10 amps. The square is 0.1 meters on 0.01 meters on a side, located 0.2 meters away from the cable. The square has a resistance of 0.001 ohms and has 200 loops. Okay, all we got to do to figure out the maximum strength of the magnetic field is just use the magnetic field of a wire formula. B field is equal to mu naught times I over 2 pi r. Okay. And so to get B max, okay, you would then get 4 pi times 10 to the negative 7, right? I don't like simplifying it, okay? So if you simplify it, right, you would obviously have something different in the numerator. I'm going to use 10 because that's that's the highest amount of current, so that's the maximum B field, okay? 2 pi, and then R, okay, is going to be 0.2, right? That's the radius. That's it looks like radius, but it's actually distance from the wire, okay, that we're measuring it at, okay? Um, and then and then we would calculate that out, right? And when you calculate that out, you should end up getting 1 times 10 to the negative fifth Teslas, okay? So that would be the maximum amount of B field that could be induced or passed through the square, okay? Then to figure out the average EMF and the average current induced during the first 2 seconds, okay, you would then need to, again, you would actually have to make a couple stops first. You would need to figure out the change in flux, which is NBA, okay, or delta NBA. One of these things is going to be changing, which would be the B field, okay. And then you would have to then go to the induced EMF equation, delta flux over delta time, and then you would have to go to Ohm's law, okay, to figure out what the current is, okay? So for the first part, okay, what I'm going to do is I need to recognize, right, that this is actually delta flux. What's changing here? N's not changing and A is not changing. So it's actually N delta B A, because B is what's changing. And we should know that B is going to fluctuate, right? We know at the most it's going to be 1 times 10 to the negative 5, okay? And at the lower end, it's going to be also negative 1 times 10 to the negative 5, right? And how do we find the total delta B, right? Delta B is actually 2 times 10 to the negative 5, and I'll show you why that is, okay? Because what's happening is here, right? This is 1 times 10 to the negative 5, okay? And then down here, because it's the same, it has the same amplitude on the bottom, right, is also going to be negative 1 times 10 to the negative 5. And the distance here, it's 1 times 10 to the negative 5 to get to 0. Then it's another 1 times 10 to the negative 5 to get back down to the opposite end. So it's actually 2 times 10 to the negative 5. Okay, you're with me on that? Okay. Okay. So then we have that, okay? So then we would plug that into the delta flux equation, okay? N that we were given is 200 loops, okay? Delta B is 2 times 10 to the negative fifth, and then the A, the area, okay, I believe the area, it's 0.01 on one side, so we would just do 0.01 squared to get the total area, okay? And you should end up getting that your delta flux is equal to, I got, what is it, 4 times 10 to the negative 7, okay, and that's in Webers, okay. And this, okay, then we can plug it into the next part of our solution, okay. So we plug this into E epsilon equals delta flux over delta T. Okay, so I got epsilon is equal to, delta flux over delta T, and we're just plugging everything in. That's 4 times 10 to the negative 7, okay, over the delta T, which is 2, and that just gives me 2 times 10 to the negative 7. Okay, that's pretty straightforward. And that's volts, right? There's our EMF, okay. Now we need to plug that into Ohm's law. So 2 times 10 to the negative 7 equals current, which we don't know yet, and then R, the resistance is 0.001. Okay, and if you calculate that out, you'll end up getting I is equal to 2 times 10 to the negative 4 amps. Okay. So there you go. There's your induced current and your induced EMF. I think that's it for this section. I don't think there's another one. Yeah, that's the next section right there. All right. Have fun. Gaslight, gatekeep, girl boss.